Hi everyone, welcome back to 128 Honest. Today, lecture 12, we're going to talk about an intro to threads, which is one of the most exciting things in Rust. So what we'll cover today we'll talk about some OS concepts, such as processes and threads, and we're going to talk about how to actually spawn threads in Rust and also how to do it properly. So this will tie into the OS concepts that we talked about earlier. So the optional reading for this lecture is the Rust book chapter 16.1, which is using threads to run code simultaneously. So first, before we talk about Rust, let's talk a bit about operating systems. So common OSs are things like Windows and Mac OS, which is what I think most people are using, and also for a lot of programmers, people also use Linux for the OS. So actually, what does the operating system do, right? So one of the key roles is resource management. So one example would be CPU time, right? For example, we have a lot of processors on our laptop. Like we have a clock, can have a browser, you can have a chat app, and they all need to take CPU time. So the OS will try to manage the resources, like which process can run first and how long it gets to take and things like that, right? Another role of the OS is for abstraction. So for example, the same Windows OS will work on different machines, right? Your laptop is not the same as mine, but we still use the same Windows OS and you can run the same programs. So that's the role of the OS. It helps to provide that abstraction layer on top of which that we can run our normal user programs. So within the OS, there's this thing called a process or processes. So what are processes actually? So actually, a process is an abstraction of one running program, right? So for example, when we have run the browser in our computer, like for example Firefox or Google Chrome, that is one process, right? And obviously we can have multiple processes running the same program. So for example, I can open like three windows of Firefox, and there will be three different processes, right? But actually they're all running the same Firefox program. So that is an example, right? So here I've listed some examples of processes such as Firefox, Discord, your text editor. It could be VS Code, it could be something like Vim, right? Even the Rust program that we are writing in this class, when we run it, it becomes a process. So then the more important thing that we're going to discuss in today's lecture are threads, right? So what exactly are threads and how are they different from processes, right? So basically, you can have multiple threads in one process. So like there's one process, but actually within it you have multiple threads. And basically threads share the address space of the program. What does this mean? So like basically it can share the variables that your program have. You can share some of the memory storage that your program has, right? So we'll look into more of this as we go on through the lecture. So one example of threads versus processes, right? So for example, we start a Discord process, right? This is one process. However, within the process, you can have multiple threads. So for example, here we have one thread for listening to new messages when you get a new message on the server. There's another thread for processing when we type on the keyboard and the Discord will show it on the screen, like if we're typing into a chat. And there's also maybe another thread to draw the different components of the UI. So the point of this illustration is to show that we have one program which runs in one process, but inside it could be multi-threaded, right? So tying all this together, we talked about operating systems, we talked about processes and threads, right? So what is the relationship? So the OS itself, like for example Windows or Linux, they're responsible for scheduling the processes and threads, right? By scheduling, I mean it determines which process get to run next on the CPU, right? It determines how long it gets to run. Because if one process runs forever, other processors won't get a chance to run, and then your system will be stuck, right? So this is an important problem in operating systems called scheduling. And in our Rust programs, when we create threads, right? If we just create threads as they are, we cannot guarantee that threads are run in a certain order because, as we said before, the operating system here will do the scheduling, right? It can decide that the thread 1 run first, followed by thread 3, followed by thread 2, and there's no way we can predict how this will happen. And if we want it to run in a certain order or direction, we have to specify it ourselves using some special constructs. So how this will actually work out will make more sense as we look at the demo later. So before we talk about making threads in Rust, the first thing we have to know is that writing multi-threaded programs in one process can create a lot of problems, right? So because, as we said before, a process can have multiple threads. but they share the information, right? So since the information can be shared, actually when different threads modify the information differently, you can have some problem with the consistency. Other problems when writing multi-threaded programs include, like for example, deadlock, where one thread that's waiting for this variable, another thread is also waiting, one thread is waiting for this other thread, thread B waits for thread A, and now since they're both waiting for each other, your program is now stuck, right? So this is called deadlock. Another example is when basically in multi-threaded program, your bugs are really difficult to reproduce, right? Your multi-threaded programs could run fine 100 times but then fail one time, and it's very hard to recreate that failure scenario in order to debug it. So here we're going to look at a toy example of what can go wrong when we're writing multi-threaded programs, right? So here we're going to have an example. Okay, for example, let's say you have a bank account. Let's say this is a really terrible bank, right? And you have a bank account with $100 inside them. That's your balance. And now you have two friends, friend A and friend B, and they both think that, okay, you are too poor, so we're going to give you $80 each, right? So you expect to have 100 plus 80 plus 80, which is you expect to have $260 at the end of this whole transaction. So here we see your friends going to the ATM to deposit money for you, right? Okay, so how this works? Say that your friends accidentally both go to the ATM at the exact same time, right? And now the ATM will ask the bank server, how much money does he have in his account, right? And the bank will say, well, he has 100, so he will send 100 to the first ATM, he will send 100 to the second ATM. Right, all this looks so good so far. Now, friend A deposits the $80 into the ATM, and since it knows that he now has 100, they know that his new balance is 100 plus 80, which is $180. So it tells the bank, okay, his new balance is $180, right? So the bank updates our balance in our account to $180. Now the second ATM previously receive the information that we have $100 in the bank, right? And it also updates the deposit of $80, and now the new balance is $180. So it sends this new information of $180 to the bank as well. So the bank will override our previous value of 180 with 180, right? So some of you will already see this problem now, which is basically that $80 is lost, right? So you expect to have $260 at the end, but because both of the ATMs thought that you have $100 initially, both of them calculated your new balance to 180, and one overrides the other, and in the end, you only get one of the deposits, right? And the bank, the ATM already took the money, so the bank steals your $80. So why is this example relevant to us? Because this is a lot of times this is what happens when you're multi-threaded programs, right? You can think of friend A and friend B here as two threads, right? And they're both trying to modify the same variable. And if we are not careful with the order in which we do the modifications, we can have problems like this. So this previous slide was an example of a race condition, right? And some of you might see it already, but the problem is you shouldn't let both ATMs know that it's $100 at the same time. You should let one update completely before you let the other one do it, right? So in Rust, they use the ownership and type system to prevent some of this concurrency problems, right? So it's called concurrency because we have multiple threads running possibly at the same time concurrently, and because Rust takes care of a lot of these concurrency problems, this aspect is commonly called fearless concurrency. So in this lecture we will go through how to make new threads, and then in subsequent lectures over the next 2 to 3 lectures we'll talk about the different techniques that Rust already has for us to deal with concurrency and make us write safe code. So this is an example where we spawn a new thread. So for firstly we need to import the standard thread library, so you just use standard thread, and this here is the most important part. So basically there's a thread spawn, right? And basically in between these two braces here, the opening one and the closing one as we define here, this is basically a function, right? So our function here is for I in 1 to 10 print this number, but essentially what you have to know is that we are creating a new thread that runs this function, okay? And in the Rust terminology, this special function that you pass in is called a closure, right? So let's look at what this function exactly does, right? It loops through I from 1 to 9, right? Because 10 is exclusive, and it will print high number 1 from the spawn thread, right? And then it will sleep for this duration from millis means sleep for 1 millisecond, and then it will print high number 2, high number 3, and so on, right? So this is the function that is passed into this new thread that we create. So what happens here is that we have the main thread when we start the program, right? And then this main thread, when we spawn, we are creating a new thread, which is spawn thread, right? But the main thread still exists, and now both of these threads will continue to execute concurrently, right? So we don't know which one will go first. We don't know whether main thread will go first or spawn thread will go first, or whether one will do one instruction, the other do one instruction, and they will interleave. So this will depend on how the operating system schedules it, like we talked about before. So let's have a demo and take a look at how this works, right? So here, let me increase the font size. So here we have the same example that we have before. We have the main function and we spawn the thread, right? Except here I'm making the thread loop from 1 to 9, and then it will print the number. And then here, this is our main function, right? Because this is not where the thread is. This is the main function. We'll print 1 to 4. We'll print high number 1 from the main thread. So basically what we expect is here they will print high number 1 from the main thread for 1, 2, 3, 4. And in the child thread, like the one that is spawned, we'll print high number 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So let's try to run it. Okay, so we see the running. So initially it says high number 1 from main thread, then it says high number 1 from spawn thread, and then 2 from main thread, 2 from spawn thread, right? So this is quite orderly, like a main and then spawn, main and then spawn. But then this doesn't always happen, right? So we can run it again, right? Okay, this looks like it's the same. Let me try to run it a few times. Okay, for example, this is a good example, right? So for example here, we have high number 1 from the main thread, then from the spawn thread, right? And until here, we see here that, it prints 2 from the spawn thread, right? It runs 2 instructions from the spawn thread, number 4 and then number 5. So the point I'm trying to make here is that there is no guarantee about which thread will run first and like in what order, right? So it's kind of random. I don't know why, but on my system it keeps showing up as the same order, but like the point is that they won't always be the same, right? For example, now it runs like this, right? Another thing we notice here is that in our spawn thread, in the child thread, we wanted to print from 1 to 9, right? We want to print high number 1, high number 2, all the way to high number 9, but this never happens, right? The spawn thread will always print at most 4 or 5, and then it will stop, right? Let's run it a few times. See, now the execution order is different again, right? And then now it only goes to 4, right? So why doesn't the spawn thread go all the way to high number 9? So I think that is the next thing that we will address. So what happened here? So basically the conclusion is that the child thread does not finish its execution, right? In the demo we noticed that the spawn thread never finished, and this is because the main thread actually finishes before the spawn thread. So and because the main thread, which is the parent thread, terminates, all the child threads that are created by the parent will terminate as well. So if we go back to here, so the main thread will split into main and the child thread, the parent thread and the child thread, and because this parent thread finishes, all the child will be forced to terminate as well, even if it's not done with its work, right? So the solution here is very simple, right? Basically we make the parent wait for the child thread to finish, and this is done using a fairly simple construct in Rust. So in Rust there's this type called a join handle, and how we use it is like this, right? When we call thread spawn, it actually returns a join handle, right? So we can just save that in a variable, so we call it handle in this case, let handle equals to thread spawn, and then somewhere before we try to finish, we can call handle.join, right? So what handle.join does is that it will cause the parent thread to block, or like to wait till the child thread finishes, right? So when the parent hits this handle.join, it will wait there until the child actually terminates, and then it will return back to here, and then the parent will continue. So let's take a look at this at this example. So here, like we do let handle equals to thread.spawn, right? So now we have the join handle type, and then here at the end we call handle.join, right? Let's save this and try to run it, right? So what we expect here to happen is that because the parent now waits for the child to finish, the child should be able to run high number 1 all the way to high number 9, right? So let's see. Okay, so ignore the warnings, and here, so we see high number 1, 2, 3, 4 from the main thread, right? And afterwards, the main thread runs 1 to 4, right? And it's done. So you see now beyond here, the main thread doesn't run anymore, but it's waiting for the child thread to finish. And the child thread does finish, it runs 4, 5, 6, 7, 8, 9, right? So this is an example of how we use the handle, which is pretty straightforward. Now, the last problem that we need to solve is in this case where we want to use the data from the main thread inside the spawn thread, right? So in this example here, we have a vector, right, that we initialize to 1, 2, 3, 4, 5. And now we want to use this vector inside there. So recall here we spawn a thread and it calls this function, right? It runs this function, it tries to print out the vector. So if we recall our ownership and borrowing rules, when this thread runs, it actually has to borrow this vector, right? So Rust will try to borrow the vector to use inside the closure, which is inside this function, right? Because, however, the problem with this approach of Rust trying to borrow it is that actually this thread, once we create it, it might outlive the parent, right? So, or it might outlive the function in which it is called. So the takeaway is that vector might not always be a valid reference, right? That at some point vector might no longer be valid, but this thread is still trying to read the vector. So one example might look like this. We call thread spawn on this vector, and then afterwards we immediately drop the vector, right? So because we don't know how the execution works, we don't have a guarantee that the thread will finish using the vector before it gets dropped, right? There's every chance that in the main thread it goes like this, and the vector variable gets dropped, it gets deleted basically. And since this is this thread tries to do a borrow, tries to get a reference to the vector, now the reference is no longer valid. So Rust will actually the compiler will complain and it will not let you do this, right? So what happens here? What happens here is that we need to use this keyword called move, right? So recall from the borrowing and ownership lecture is that when you move, you are transferring basically the ownership from here, which is in the parent thread, into the closure, right? So that's called a move. We move from the parent thread into the closure. And when we call thread spawn with this move, it says that it means that whatever data that is used in the closure that is part of the parent, we'll move it into the closure. That means here, if we try to use the vector again from the parent, we can't use it anymore because the ownership has already been moved in, right? So let's try to see a demo of that. So say here, we define the vector 1, 2, 3, 4, 5. Okay, and then here let's say we use the vector here, right? We print out the vector. Here we don't need this anymore. Okay, so here is a simple example, right? We create a vector here. We create a thread that uses the same vector inside, and then we use handle.join to wait for the child to finish, right? So what happens if we try to compile this? So let's try to run a cargo build. We can see that it doesn't compile, right? So, and why? So let's see the error message. It says closure may outlive the current function, but it borrows the vector. So he's saying that this closure is trying to borrow the vector, but it might actually outlive this function, right? So the Rust compiler here is actually very helpful. It actually says to force the closure to take ownership, use the move keyword, and it even tells you exactly where to put it, which is here, right? After the thread spawn, use the word move. So let's try that. So now that we have the move keyword, let's save and let's try to build it again. So let's do cargo build, and we see now that it builds successfully, right? And if we run cargo run, it will just print out the vector. Yeah, so as we see here, it prints out the vector, and this is fine. So yeah, the move keyword ensures that we move any data that is used in the closure from outside into the closure, right? And it's a transfer of ownership. So to recap, we've talked about processes and threads. A process can have multiple threads, and here we're learning about making multi-threaded programs. Spawning threads is done with this thread : spawn, and you want to wait for the child to finish, you use handle.join. And lastly, about ownership rules, you'll use move when you're passing data into the closure, which will take ownership. So some announcements. Homework 10 is released today on Prairie Learn and will be due next Saturday at 2359. Also, earlier this week we released the final project with the project document. So do take a look at it if you haven't. But the first deadline coming up is to form groups and to think of project ideas. We have a team building and channel in the Discord for you to like try to look for like-minded people and form groups and also discuss ideas. And we also have our first, not first, but like the first kind of official in-person discussion session this Sunday from 5 to 7 p.m. in Cibo 1404. So this is not compulsory, but it's a good way for you to come and meet the core staff and like talk to other people to form groups and get help with homework. And we're going to have like a short like review of the content in class as well. So yeah, we hope to see everyone there and have fun coding Rust.